Hi. Meditation is a practice that aims at self-inducing a state of calm and rest, usually for relaxation and concentration purposes. Meditation has been proved to have effects on the control of stressful situations. In this work, we analyze physiological signals collected with wearable sensors to observe if meditation has a noticeable effect on the human body's response. In this presentation, we will explain hints to detect meditation using this type of widely extended self-monitoring sensors. I am Constantino Alvarez, a PhD student at the Center for Machine Vision and Signal Analysis at the University of Oulu in Finland, and this work has been done in collaboration with the Center for Ubiquitous Computing, also here at the University of Oulu. The first question we have asked ourselves when studying the detection of stress was the possibility of using the same sensors and physiological signals to detect meditation as a self-induced state of calm. How this kind of guided meditation could affect our body's response in terms of physiological changes. So, the research question had as main objective to detect or to know if we can detect this activity as a real impact in our body parameters. In addition, the research was focused on the detection using sensors from wearable devices because of the success of these devices among most of the population in the recent years. After studying the state-of-the-art related to stress detection using these devices, we have adopted a similar approach to the one used in most of the relevant papers. There are also recent approaches using neural networks, but we wanted to use a known and clear approach to compare our meditation results with the results on stress detection. This decision was also motivated by the trade-off between performance and efficiency, thinking its implementation for real-time processing on embedded systems, most of the available wearables in the market. To do this, we have used publicly available databases that contain this type of affective state, guided meditation, among other common affective states, and biosignals. For this paper, we have used a well-known multimodal database called WESAD, from Wearable Stress and Affect Detection, whose main purpose is the classification of stress against amusement and neutral affective state, the baseline in this database. Additionally, they have in the protocol a fourth state called meditation, where they have guided the subjects in the database through a series of meditation exercises to calm them down. The database contains 15 subjects, 2 devices, as we can see, and 2 different protocols. It was recorded using a more accurate but bulky chest device, which we have discarded, and a well-known wrist-worn device widely used in the researching, and with similar sensors to those that we can find in commercial wrist-worn wearables. So all the physiological signals used to answer our research questions come from this device called Empatica E4. As we can see in the current slide, we have used a traditional and standard training pipeline divided in 2 main steps to generate our models. A critical stage of preprocessing where the signals are visualized, cleaned, and processed, filtered, decomposed, etc., to extract our filters, which will be used in the next step, the training stage. As already mentioned, we have used only the signals from the wrist device, which are in general more challenging than the signals recorded with the chest device, due to the quality of the sensors in the devices and the movements of the arms and hands on the subjects, as shown in the left corner plot of the accelerometer signals. After the preprocessing step, we have chunked every signal in windows of different lengths and a fixed overlap time to extract distinctive filters in the time domain and in the frequency domain. As a result, we have several vectors, total number of windows, with values our filters for each affective stage and per user, as we can see in the table in the current slide. So for every window we have extracted in total 110 filters, including statistical and physiological filters related to the heart. One of the main differences with the previous works is the focus on those filters related with the heart rate variability. We have added around 30 additional filters in that sense. Another difference comes from the algorithm used to decompose the electrodermal activity signal, where we have used an extra component called pseudomotor net activity as NNA. To choose our classifier algorithm, we have used a Python library called LazyPredict, which gives us the possibility of training up to 40 different classifiers at one time. This package is a wrapper based on the well-known scikit-learn Python package as well. After the first experiments and considering the results and experiments done in the original WESAP paper, we have selected 6 different classifiers belonging to 3 diverse types of classifiers, 2 based on trees, 2 based on linear classification, and 2 classifiers based on stochastic gradient descent classification. With all this, we have performed 2 types of classification, a binary classification and a 3 classes classification. For the binary classification, we have performed 3 different experiments: the classification between stress versus non-stress, classification between meditation and non-meditation, and the most challenging one, but the most interesting at the same time, the binary classification between meditation and a neutral state, 2 close states in the emotion classification scale. The evaluation always is a critical part, especially when we have few subjects and high variance. And in this case, we have opted by using a leave one subject out cross-validation by training 15 different models and computing the mean of the balance accuracy and its standard deviation as metric. Realize that we have used balance accuracy a fairer metric in this situation because in the most of the studies found in the literature, authors use simple accuracy. From this slide onwards, I will show you quickly some of the tables with the results of some of the performed experiments. We show here the results using windows of 120 seconds as representative results. For every table, we have in the columns the results for each classifier, and in the rows the results for each modality where we combine different signals. The first 3 slides show the results for the binary classification between stress and non-stress affective states, with a slightly difference related to the input filters. We achieved very good prediction results among all the users in the database, especially in those modalities which combine the heart rate variability filters, in which this work has especially been focused and has extended. The same experiment, but applying normalization, worsens slightly the previous results for this binary classification. And in this current slide, we include the median statistical filter for every signal and the extra component of the electrodermal activity signal without normalization, which in this case does not improve the previous results. In the next 3 slides, we show the results for the classification between meditation versus non-meditation, a combination of windows of stress and amusement affective states. In theory, an easier task because the distance among the affective states in terms of arousal and balance. We can observe again that the best results come from those modalities and signal combinations containing the heart rate variability filters that we have extended. For this same experiment, but normalizing the input filters, in general the results are slightly worse, except for the modality which contain the skin temperature signal, which improved the results a little bit related to the previous results. But for this experiment, the best improvement comes when including the median statistical filter and the extra electrodermal activity component in a modality that includes the EDA signal, the heart rate variability filters together with the blood volume pulse signal. In the next 3 slides, we show the results for the binary classification between meditation versus a neutral affective state, the most interesting experiment towards a proper meditation detection. Notice that we are trying to classify here two very close affective states, which makes the classification more challenging as previously mentioned in comparison with the previous experiments. Also notice that in this classification the accelerometer sensor plays an important role for obvious reasons. During the guided meditation, we have our bodies totally static during some period of time, while not necessary in a neutral state. But also notice that the other modality that plays an important role here in this classification is the which one related to the heart rate variability filters, and where we put more attention as an indicative of a proper meditation state. For this experiment, the normalization improves slightly all the results among all the classifiers, but without overtaking the previous results. For this classification, the best results come when including again the pseudomotor nerve activity component and the median statistical filter of all the signals. The best modality includes the EDA signal, the accelerometer signals, and the heart rate variability filters. When we use only one sensor, the best results for this database come from the accelerometer sensor, closely followed by the heart rate variability filters from the BBP sensor. In the next slides, we show quickly the three classes classification experiments, where at first, for comparison purposes with other literature works, we try to classify among baseline at the neutral state of the database, stress, and amusement affective state. Obviously, this classification is more challenging than the binary classification, but we have improved slightly the results from the previous works for this type of classification. The improvements come also from the modalities which include the heart rate variability filters and the extra component from the EDA signal. The experiment where we try to classify among meditation, stress, and amusement affective states shows similar results than when using baseline instead of meditation, but slightly improved numbers. So we can say that it is easier to detect meditation than baseline when we do three classes inference. As conclusion, we can say that we can detect meditation using wearable devices with a relatively good accuracy. We achieve around 87% of accuracy in the experiments involving meditation detection. And we bring for first time in the literature the classification between meditation as self-induced state of calm and a neutral casual state. In general, we improve the results in the literature with similar approaches, and the best results for us come when using windows of 120 seconds. Some of the findings are that in general classifiers based on trees were better, especially the extra trees classifier, and the normalization doesn't improve in general the results except for the random forest classifier. Obviously, it's more difficult to classify meditation than stress, and the binary classification is easier than the three-class classification. Here we can see the general or the summary of the results for every classification modality in the window size. As future work, we want to continue exploring, researching in the explainability of those filters, especially related with the heart rate variability, by doing some sub-values or filter importance analysis. Related to the classifiers, we want to work or improve the results by doing some ensemble of classifiers, also continue exploring the deep learning approaches, and using or applying our methodology in other databases. And also we want to work in the real-time implementation by studying the trade-offs between accuracy, number of signals, number of operation, energy consumption, etc., and doing this implementation in some embedded device. So thanks for attending to this presentation, and I am open to whatever question you have.